Okay, thank you, Yann. So apologies for speaking in English. My French really isn't quite up to doing a full talk in it. Okay, so as Yann was saying, I'm going to talk today about memory in neural networks. And I think it's an interesting topic. There are many tasks out there in the world that you want to perform that do require some kind of memory. And that the traditional neural network models that have proven so effective at, in recent times, things like convnets and recurrent nets, aren't actually all that good, as we'll see, at remembering things. And particularly when we have very large inputs, which we will in certain settings. Also if only some parts of that input are actually relevant. So as a result, there's been quite a lot of papers come out in the last year or two that have looked at trying to add memory in some fashion to a neural network. And today, I'm going to go through a series of those works. So we're just going to start off with looking at the sort of traditional models and seeing how they do actually have some ability to memorize things. And then we'll look at models where people have deliberately sort of added in some kind of external memory unit. Okay, so my laser pointer doesn't work. Okay, so I guess I'll just use the mouse pointer. So I'm going to go through each of these in a little bit of depth and then talk about some related work. And then finally at the end, I'll talk about another type of memory that people use, which requires slightly different sort of underlying model because of the way it operates. Okay, so let's just start off by thinking about Yann's finding a laser pointer for me. All right, perfect, thank you. So let's just start by thinking about a recurrent neural net. So Yann tells me that in previous lectures, people have covered this. So the idea is you've got some sort of hidden state that is going to be passed, through some transformation each time step. And there'll be some input signal which will be combined with the hidden state from the previous time step. Now, so this model is capable of basically having, remembering things. So what I mean by that is if you have some event that happened way back in the past, some input back here, that will affect the hidden state way back. And of course, if this hidden state's propagating, there'll be some sort of trace of that event that happened a long time in the past at the current time step. So in that sense, it has sort of, in quotes, remembered that event that happened way back. Now, the catch is that, of course, this model is using, the only thing it really has to sort of carry that information is the hidden state. So it's mixing both the computation and memory within that hidden state vector. And the problem is, of course, that if the output from the RNN has to do some sort of quite complicated computation, that's going to require many layers of nonlinearity. And of course, those nonlinearities may affect the information that you have in that hidden state. So they might sort of attenuate it over time. So it's going to get lost. The information over time will get lost. And there's also, of course, the issue that inherent with RNNs, which hopefully people have explained previously, that when you're trying to train these things, it's very difficult to do it. When you backpropagate during training, it's hard to backpropagate more than a certain number of steps in the past. Because the gradients either kind of vanish or explode depending on the eigenvalue structure of the state transition matrix that you have. So as a result, there's a sort of little, there's a whole range of different approaches for trying to fix these recurrent net models. Okay, and the most, one simple approach is to try and modify the way that hidden state evolves. So that state transition matrix, you can try and constrain it in some way, so that some parts of it are allowed to change quickly, which makes sense for doing sort of computation. And then there might be other parts of the state where you deliberately impede change. So that can be, you can think of that as being a good part of the hidden state to store information from things way in the past. The other family of approaches looks at trying to introduce some kind of gating. That is some way of sort of locking some parts of that hidden state and so there's a lot of, one very popular recent approach is this long short-term memory. So you can think of this, it has a sort of series of gating functions, which in some sense means that the memory cells act as little sort of bistable logic units, if you're sort of from a EE background. And they're able to kind of essentially lock that state and only reset it at some point in the future. But in the intervening time, you can read it out with with no degradation over time. And there are sort of various variants of that LSTM model as well that people have been looking at recently. But there are some basic inherent problems. So your memory capacity is somewhat fixed by the size of that state vector. And then you've got some sort of the computation time. So if you obviously might want to have more memory, you can make that state vector bigger. But then you've got the difficulty that the computation time is going to be n squared because you're going to have to do this matrix multiplication at every time step. And there's no way of sort of selecting pieces of that state vector. You have to kind of look at it, the whole vector at once at each time step. Okay, so nevertheless, these models are actually pretty effective. And in the various new approaches I'm going to discuss, these, the RNNs and LSTMs form a sort of very competitive baseline method that we will see. Okay, so now I'm going to spend some time, the main sort of meat of this is going to be going through these three different approaches to kind of adding external memory. And the basic point is to sort of to have your existing model, which will be something like an RNN or an LSTM, but now you're going to have an external memory module, okay? And the controller, which is sometimes called, is going to be able to sort of read and write from that memory module. And that memory might be initialized with, say, a bunch of inputs. And so this controller will then have the luxury of kind of accessing the inputs at any point. And so the state of this will be updated over time in some of the models. But generally, the point is that the computation part's happening over here and the storage part's happening over here. There's a bunch of different ways. Obviously, this is a very general architecture I'm describing. There's a bunch of ways you can actually instantiate that. So obviously you need some way of interacting with some small piece of the memory. It's very unlikely that all the items in memory are going to be useful for you. So you need some kind of addressing mechanism. And there's a couple of ways of doing that. So you can imagine in a computer, of course, you have a hard address. You access a single memory location at a given time. So you can do that. But of course, the problem is that then it becomes difficult to train these models. You can't use backpropagation because that memory module isn't a sort of continuous thing you can pass gradients through. So at the very end, we'll look at one approach which does use some sort of hard addressing idea, and we have to train it with reinforcement learning rather than backpropagation. So quite a few of the models, the next few models I'm going to describe all actually use some kind of soft addressing. So that is, technically they're touching all the memories at any given time step, but in practice there'll be some weighting over them. So you're sort of focusing some attention on a subset of those memories, or those memory locations. And then in terms of the other thing that you can have is you can have addressing based on context. That is, you might have some kind of associative memory. You have a vector, and you want to find similar vectors in the memory. That's one method. And then the sort of more traditional sense of memory, which you have in a computer, is sort of location-based. So you might say, I want to access whatever's in a particular spatial location in memory. But these two actually can be combined to some extent. There are ways to kind of augment the items stored in memory that include some representation of where they are, and then essentially it becomes more similar to this sort of context-based addressing. So we'll look at, we'll discuss one approach in detail that does just that. Okay, so the first model I'm going to talk about is something called a stack RNN. So this was a recent paper from some colleagues at Facebook Research, Armand Julin and Thomas Mikolov. And this is essentially just a simple RNN model where they've augmented it with a stack. So this is a standard computer science data structure which you can use for storing things. And the idea itself has been around for a very long time. I think this in some sense, but they've this new paper sort of benefited from the advances in computation and data size and things like that. Now they actually decided that they were going to try and instead of tackling the sort of traditional problems that people worry about, they were looking at these sort of quite complicated toy patterns. They were going to try and train them without too much supervision. So I'll just in a moment explain what I mean by the particular problems. But let's just look at the model. So this is the top part here is the standard recurrent net. And what's different is that they have a stack attached to it, okay? And in each time step, they have the ability to decide whether they're going to sort of push, so they're going to pop an item from the stack, which will then be, through this transformation P, will influence the hidden state at the current time. And then that's at the next time step, essentially, you'll then decide to have an action, which is going to be actually a continuous vector over 3 possible things that you'll do with the stack at the next time step. So you'll either do nothing, you'll either push the current state, ht, onto the stack through the matrix D, or you'll pop, or you won't put the item on, but you'll just pop it at the next time step. Okay, so there's going to be a sort of 3-vector of AT is going to be a 3-vector that sort of sums to 1, so it's continuous, and that's going to essentially control the behavior of this stack. Now the key point is that they're not going to, that the model will, they have to train the behavior of this pathway. They have to train the model so that it doesn't, that it learns how to use this stack interface. So that is, there's no explicit label saying, okay, at this time step you should store something on the stack. All that's going to happen is that the model's going to be trying to predict the next symbol in a sequence, which I'll show you in a moment, and if the error signal from that prediction is going to be used to update all the different matrices that you see here, U, V, P, D, and A, and these ones at the bottom effectively control the sort of operation of the stack, both the way you kind of read from it and how what action you're going to take, and then how you push to it and things like that. Now, in this diagram, there's only just one stack. In practice, to solve any kind of interesting problem, you might need to have multiple stacks. They, in fact, can train with quite a large number of these in the model, okay? So let's just look at the problems they tried to solve. So this is actually, they've decided to try and tackle these sort of sequences of repeating symbols. So just to take the top one as an example, so this, the n here is some integer. So for example, in this little sequence, n is 2. So you can see here you have, oh, I'm sorry, n may vary in this particular example. So in this case here, initially it's just 2 A's, then 2 B's, then it's 3 A's, then 3 B's, then 1 A, 1 B, and in this case I think it's 5 A's, 5 B's. And what the model has to do is to go along and try and predict the next symbol, and they measure how well it's doing, and then sort of get some error signal from that on the ones in bold. So these are ones that you have some hope of predicting. So if you've seen 2 A's and then you transition to a B, you know that you're supposed to have 2 B's, so therefore the next symbol should be a B. But then the following symbol after that has to be an A again, right? Because you only had 2 A's, so you should only have 2 B's. And then you have to revert to the other symbol. And so in this way, they're going to train, effectively, we're just trying to predict the next symbol in the sequence. This is sort of alludes to what Yann was saying in his talk about prediction being a sort of important way of training. Now, so just to show an example of this thing running, so this is the sequence, this is a trained model. We use it running on the sequence A6, B12. So this means effectively you can have 6 A's, then 12 B's. And that you can see this particular model, they've got 2 stacks. And the first stack is effectively counting the number of A's. So it's doing push, 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 push 6 times. And then thereafter it starts popping off the stack. And then the second stack is going to sort of handle the B's. So this thing effectively counts, pushes on 12 times and then starts popping off. So this gives the model an ability to essentially keep track of how many times each of these symbols is appearing. And then the output from the stack, of course, will influence the hidden state, which of course will determine the output at each given time step. So effectively, these are a bunch of sort of counting problems. Essentially, you're seeing whether these models can remember how many instances of each symbol they've seen, and then in some sort of fixed pattern, and then reproduce it. So you can see that the standard RNN model does pretty poorly. Okay, so this is some sort of accuracy, so higher is better. Now the LSTMs, which do, as I mentioned, these are RNNs which have some kind of gating for each unit, so they do actually have some ability to kind of count. It would seem, based on these numbers, but they do struggle a little bit on some of the harder ones. We have more symbols, or you have slightly more complicated patterns. And then this particular model I just described, the stack RNN, where you have the stack, seems to do pretty well. And of course, the point is that once the item's popped onto that stack, there's nothing that's going to actually, it doesn't degrade. The items don't sort of atrophy over time like they would in the hidden state of an RNN or something like that. But you can use these models for more than just counting. So they also tried, this is just for memorizing long sequences of arbitrary symbols. So here you can see that now the LSTM, does better than an RNN. So this is the length of the sequence here, and this is the accuracy. So as the sequences get longer, obviously it's harder to remember. An RNN drops off quite quickly. The LSTM does a bit better, and then they have this stack model is the red one at the top. And they also tried a list data structure as well, which didn't seem to work quite as well. That's in blue. And they also were able to train it to solve simple sort of algorithmic tasks. So in this particular case, this was the problem was binary addition. So of course, to do that, you have to actually, you do require memory. You have to remember the carry and propagate that across multiple, columns in some sense of the you've got multiple digits and you need to propagate that carry along. So here you can see that the LSTM does barely better than the RNN, but then this stack RNN model does quite well and does start falling off once the digits get really long. So this is just an example, a little bit illustration of them actually doing doing the binary addition. So they're given the training time, they're given these sequences of numbers. I guess they have an addition symbol indicating the end of each, or the separation between the two numbers, and then they're given the sort of output sequence. And so when they mean no supervision, what they mean is that it's not like there's no supervision saying how the model should use these 10 stacks. It's all the use of those stacks has been learned through backpropagation by trying to predict the next symbol. And you can see here that when they sort of looked inside the model, they were able to see that there was one of the stacks effectively was keeping track of that carry operation that you need to be able to do addition successfully. So so what you can see that once you have memory, you are actually able to get these models to do some quite interesting things. Okay, so just to summarize this model, so it's able to learn some of these algorithmic patterns, and it does have true long-term memory. That stack's going to hold things essentially indefinitely, and they were able to get it to work for some toy problems that do break these existing models. The catch is that it's not a hugely efficient model. There's obviously quite a lot of machinery in operating that stack. And of course, the stack is one particular type of interface, one type of particular memory interface. And it's a little bit unclear that that's necessarily the most general one for other types of problem. Okay, so the next model I'm going to talk about is something called a memory network. So this has a different memory interface. This is some work that I was involved with one of my students at NYU, Sina. And the motivation for this particular model is that some of the existing models we have are quite well adapted to certain types of data structure within the data. So if you have, if the data lies on some spatial grid, be it in 2D or 3D, the convnets that Yann came up with work very well. If you have a temporal sequence, then the RNNs make quite a lot of sense, or RNNs with some kind of, either gating or some kind of stack structure work quite well. But there are many problems where you do need to actually access things completely out of order, or maybe there isn't any inherent ordering in your input. So just to give you an example of a kind of problem like that, so here's a little question and answering problem. So we're given a series of sentences that just in simple English, and then we're given a question, which is where was the apple after the garden? And to answer this, you need to access different sentences within this. Many of these are irrelevant, but so if you just trace what you have to look at to correctly respond to this, you have to first of all understand that you're talking about an apple, where there's a sentence talking about apples, and then the Sam is involved with the sentence, so you have to find where Sam appears. So he appears here, and then you also then see that he also appears here too. So the point is to correctly answer this, you actually have to kind of access different sentences out of order. There's no inherent sequence like you would have in some sort of temporal signal. And so in this memory network model, effectively what we're going to do is to have an associative type memory where we're going to address based on the current content at each memory location. And it's going to be continuous memory access pattern. So that is what I mean by this, is we're going to have we're going to look at all the different memory entries at each time step, and we're going to attend to in some weighted fashion just to a subset of them. And we will also have the ability to do multiple memory lookups. So we're not just doing a single memory access. You can see in the previous example, you needed not just a single memory access, we needed 3 of them to correctly answer the question. So we'll need to have the ability to do this. And because everything's sort of continuous, we will be able to train with backpropagation still. And that turns out to make the training fairly straightforward. So for various reasons, this thing's called an end-to-end memory network, as I'll describe in a moment. So, sorry, I guess it's here. So the main motivation is that it's an extension of the original memory networks concept that came out of, was Jason Weston, Sumit Chopra, and Antoine Board came up with just a year or two ago. So this model was different in the sense they had hard attention. So it only looked at a single memory location at each time step. And the problem with that is, during training, you had to sort of explicitly say which memory it should be looking at. And of course, that's quite restrictive. For some simple tasks, you might have that kind of information available. But in more general settings, you won't know exactly what memory location is going to be relevant, or it's too cumbersome to supply it. So in contrast, in this work, we would only need to provide the answer to the question during training. We wouldn't need to, in this example back here, we wouldn't need to say that these three memories are important. We just would need to give the response, and the model would figure out that those three locations are the right ones to examine. Right. So in some sense, yeah, so this model I'm about to describe is a soft version of this thing. So we no longer have the hard attention, we have a soft attention over all memory locations. So just to see what's going on, we have this controller module on the right side, we have a memory module on the left rather. We have an input here of essentially memory vectors. So I'll describe in a moment how we generate those, and these will have no inherent ordering to them. And then we have some initial state of our controller. So you can think of this as an RNN. So this is the hidden state of your RNN. And what we're going to do is to use that hidden state to access the elements of this memory. And I'll describe how exactly we do that in just a second. And then that will give us a vector that we read back from the memory and add to the current hidden state to update it, to make U2. And that's what we call hop, where we address into the memory and then read back from it. And we're going to do that multiple times, potentially, before we get up to the top of the model, and then we're going to have some simple output. So for example, in that question and answering task, the output here will be something like a softmax over a small discrete vocabulary of possible answers. And the input to that softmax will be the hidden state at the third time step. So just to see what goes on inside this module, so I'm going to look at one of the addressing operation and then the read operation. So here are the memory vectors. We're going to take the addressing signal from this is effectively the state of the controller, or the RNN if you want to think about it. And what we're going to do is a simple dot product between this state and these memory vectors. So when we do a dot product, we're going to get a bunch of scalars, which we can then put through a softmax to sort of normalize them. So we're now going to have a bunch of numbers. If we have n memory vectors, we'll have a vector of n scalars, and they will sum to 1. You can think of these effectively as attention weights. So the idea is that if this particular, say, M2 is close to U, then this will have a large value at this output of the softmax. Okay? And if it's somewhat irrelevant, then the dot product will be very small, so you'll end up with very small numbers here. So that's effectively tells us sort of where we're looking in the memory. That's the soft attention I was referring to. Now what we're going to do is to read out from it, and what we're going to do is to effectively sum up these vectors weighted by each of the attention weights. Okay, so this is going to result then in a sort of weighted memory vector that we pass back to the controller, and that will be used to update the state. Okay, so it's a very simple operation. So you can see all of this as sort of, it's simple linear algebra. So with all this, you can backpropagate through all these operations fairly straightforwardly. So just to describe now how we get those memory vectors in the first place, well, if we're dealing with that little example I showed where we have this question and answering task, you have a little sentence, Sam drops apple, and the idea is that each of these words will have an embedding vector v, and we're going to do a simple bag of words approach where we just simply add up those vectors, and that would produce the memory vector for that sentence. Now in this model, when we backpropagate, we're actually learning these embedding vectors. Okay, so the parameters in this model are the parameters in the controller and the embedding vectors here, which make up the words basically in the sentences. So that's what we're learning in the model. Now, if you do want to encode some kind of temporal information, so if there was some ordering to the sentences, so for example, in this particular example, it does matter where Sam, the order in which Sam visited different locations, then you can add that information by essentially having a kind of extra, word, as it were, for different times. So this is an embedding of the word for sort of time 3, if you like. And that will also be trained as well. And we would just add that in the bag of words representation to make the third memory vector. Okay, so just to see how we put it all together, to run it through for that little example for the question and answering. So each of those sentences through that bag of words approach is going to become a different memory vector. You've got the question, so that will also be embedded through some in representation that we learn to create this hidden state, initial hidden state of the controller U1. And then we're going to do our little dot product and softmax operation, and then we get some kind of weighting out of that across the different memories, the different elements, the different memory vectors that we have. And then our weighted sum output is going to be this. Okay, so we're going to use those weights to weight each of these, and that is going to be passed back to, we're going to add that to U1 to create U2, and then we'll pass into some sort of output function. In this case, there's only one memory hop. In practice, we're going to use, say, 3 memory hops or something like that for various problems. And just to contrast it with the original memory networks paper, so here what they did was they did the same dot product operation. So it's still this essentially content-based indexing that they're using to access the different memories, but they're going to do an argmax. So this is a hard operation which gives you a single location, which then will pick out, in this case, element k from the different memory vectors, which will be passed back. And the difficulty is that you can't basically differentiate through this thing, so you can't backprop. And just to look at, so there's actually a bunch of related pieces of work I'll just quickly go through on this. So there's the idea of this is a model that uses an encoded-decoded structure. So it's an RNN-based model, which does also have attention. And then they have, as I mentioned, this is the stack model I just described in RNNs. There's this neural Turing machine approach, which I'll describe in just a minute. And it's important to recognize that people have thought about doing this sort of thing for a very long time. So there's actually some old papers from the 90s in the previous sort of era when neural nets were popular, where people tried to do these things, but they didn't sort of actually get them working on real problems. And then since the Memory Networks paper, there's been a whole bunch of sort of very similar papers where people have tried to do the same kind of thing. So just to look at now some experiments with this, so that we took these Babi tasks, so these are simple problems designed to sort of explore different types of reasoning, and the idea is they all take this format of being given a bunch of sentences, and then you're given a question, and then you need to provide the answer. Okay, and the answer is typically a single words. The idea is, and so these were introduced by Jason Weston and other people at Facebook. And so some of them, to show the types of reasoning you have here, so this is one where you have some kind of induction, so you ask what color's Brian, and you have to realize that, well, Brian's a lion, Julius is a lion, and Julius happens to be white. Okay, so there you give the answer white. And so there's about 20 of these different problems. So this is one type. Other ones involve just temporal ordering. Other ones involve counting and things like that. And the training set size is in the order of sort of 1,000 for each type of task. And there are so 20,000 sentences in the smaller set, or 10,000 in the larger. So just to look at the results, so what we're showing here is the fraction of tasks where the model failed. And by failed, we mean it got more than a few % error. Now, in the original Memory Networks paper, they essentially had this extra level of supervision where they knew which memories were important. So, for example, in this example, they would know that this last sentence was irrelevant, and that they should have, they needed to look at, this one first, then this one, then this one. So that level of extra supervision meant the original model, fails on 2 out of the 20 if you have the larger training set. But then, of course, we're interested in this weaker supervised setting where you don't have that ground truth attention. You have to the model has to learn to what it should attend to. So an LSTM does quite badly. So it fails on all but 4 of the tasks. And then the memory network, the end-to-end version, you can see that the basic version succeeds on about half of them. And if you add in sort of various bells and whistles to the model, you can actually get it pretty close to the fully supervised case up there. Just to show a few more details, so this is the various sort of refinements. You can put some positional encoding, that encodes some kind of ordering. There's various sort of tricks you can do with adding noise in the model, and then also if you train across all 20 tasks simultaneously, that also ends up helping as well, at least if you have a smaller data set. And so you can see all these things reduce your error, your average error across the different tasks. And as you might hope, if you have more of these memory access operations available within the model, that will decrease the errors. If you just have a single memory access, then some of these tasks are impossible to solve, so you end up doing not very well. But if you add in more memory hops, then the error rate comes down. Unfortunately, at least for these problems, going to more than 4 hops doesn't really do too much. So this is just showing you an example of one of those little induction problems. And what we're showing here is the 3 different memory hops. And this is the attention vector. That's the output of that softmax over the different memories. Each of these is going to be a separate memory vector. And you can see essentially what it's looking at. So it's able to basically solve these simple kind of reasoning problems by attending to different elements in memory and then giving the right answer. So you can see this gives the right answer here. And this case is one where there's only 2, it only needs to attend to 2 sentences, but we have 3 hops, but that doesn't sort of break the model. It just does a redundant kind of access, in the middle somewhere. Now these models are quite flexible, so you can, this is just one particular task. You can also apply them to other more standard things like language modeling. So in language modeling, you're given a sentence, you're given a stream of text, and you need to predict the next word. So for example, if the previous words were, Yann says your model must be, and then if you know something about Yann, you might have a guess at what the next word should be. And the idea is that, at least in this setting, each word is going to be a separate memory. Okay, so previously we had each sentence was a separate memory. Now we're just going to do it at the word level. And we do, in fact, keep a record of the ordering within each memory vector's representation. And then the controller, can access essentially any of the words it's seen previously to decide what the next one should be. And these are sort of standard data sets that we used. And if you just increase the number of memory hops, this is perplexity, which is the measure they use for performance in language modeling on the test set. So roughly you can think about perplexity as being the size of the vocabulary that the model essentially has for that next word. So if it was a perfect model, the size of that vocabulary would be 1. In practice here, you can see it's around 100 different words it thinks are plausible at each time step. So you can see this is an LSTM baseline. So the LSTM models have been very highly tuned on these kind of benchmarks. So you can see that the memory network does sort of comparably well. This is a harder, bigger language modeling data set. So the perplexity is a bit higher in absolute terms, but you can see that the memory network does roughly at least as well as the LSTM. And this is just showing you the effect of increasing the memory size. So obviously, the bigger the memory, the more words you can store from previously. So it should, of course, help having more context to predict the next word. And that's what you see, indeed, that once the memory is sufficiently big, it does pretty well. Here, I guess, it's a tougher data set. It seems to sort of marginally help. And we can visualize the attention. So this is using a memory of size 100. So this is the most recent word here. And this is the output of that softmax vector at the different memory hops. So there are 6 memory hops in this model. And this is the oldest word, 100 words previously. And this is the immediately preceding word. And you can see that at the first hop, it kind of attends to the last few words. You can see most of white is higher weight, black is lower. And then the next hop, it somehow looks back at all the words previously with somewhat equal weight. All right, so this is sort of getting a sort of overall context. And then it goes back to looking at, say, the last 10 words or so, and then it flicks back and starts looking at all of them again. So it has this funny, it seems to learn this funny alternating attention between, immediately local information and this global look at the entire memory. Okay. Now, it's also possible to, so far in this model, we've effectively used it just for reading. That is, all the sentences were placed in memory at the outset, and we were just accessing different portions of them at any given time step. But it's possible to also actually update the memory too. So the part we've seen so far was this box, and this box. Now, the bit that is the new piece here is this write module. So you can take the controller state and you can outer product it with some kind of attention vector instead of doing the inner product operation. And that will give you essentially a matrix which you will add to your current set of memory vectors. And that's one simple mechanism for updating the memory. Again, it's all simple sort of differentiable operations, so you can backpropagate through this whole thing. And just to be clear, that the supervision is only going to be, again, at the output, so we won't have anything saying what it is that we're actually going to, we should be writing in every given time step. The model has to learn for itself what it should write. And the attention mechanism here is basically the same as we had for the read module. So this is kind of, you're essentially doing inner products with between the controller state and the memory. So you can actually do some interesting things, like you can actually get it to sort small sequences of numbers. So in this case, what we start off with certain numbers loaded into the one portion of the memory, and then we have another portion of the memory that we're going to use for output. And effectively, what's going to happen is there are two attention vectors now. There's one for reading different parts of the memory, and there's one for writing. So initially, we start off, it reads these two values, so 10 and 12, and then the model decides to basically only write to the 10 to this particular slot. And then the next time step, it attends to 12 and then writes to the next slot, the value 12. Of course, it's not, in fact, it's the value 12, it's the embedding vector that corresponds to 12. So it's always writing. Every entry in memory is not is actual a sort of a multi-dimensional vector. And so it's a little bit some of these things are a little bit mysterious exactly what it's doing, but you can see as you run the model forward, it is able to reorder those inputs basically. So it's able to take those ones on the left side and reorder them as you can see on the right here. So it does so it's not like it's learnt any kind of quick sort or bubble sort or any algorithm like that. It's simply able to kind of sort of search exhaustively through all the elements and then find them in increasing order. Okay, so this is a different type of interface from the stack RNN that we saw. So in the stack RNN, we had this very prescribed way of accessing the memory. We could only push and pop from the very top of the stack. In this case, you can access any of the memory locations you want with this soft attention mechanism, and you can train the whole thing with backpropagation. So it seems to work pretty well on these little toy question and answering tasks, and works about as well as an LSTM on the language modeling. And we have been using it for quite a few other things, like learning to play simple video games and stuff like that, where you need to be able to sort of, the attention corresponds to looking at different parts of the game state. You might attend to different characters within the sort of the 2D adventure game or something like that. So if you want to try it out, there's code online in a couple of different languages, in fact. Okay, so the last one I'm going to talk about in this section is the neural Turing machine. So this is actually a pretty cool piece of work. So this is quite a complicated model where they have essentially tapes, which, again, it's a continuous memory, just like we had in the memory network. You have a bunch of read heads and write heads. They actually have different types of addressing. So they have the content-based addressing like you have in the memory network, but they also have a location-based addressing too. So they're able to sort of say, okay, I want to access the memory location 1 over from the previous one. And the controller in this case they're going to use an LSTM for that. They also did try a simple feed-forward model. And again, it's all differentiable, and the addressing mechanism is soft, so they can train with backpropagation. The model is quite elaborate. So just to show it in operation, so this is where they're given the inputs are going to be sort of these binary vectors at each so that time is on the x-axis, and each time step you're going to be given a binary vector, and you have to sort of produce that at the output. And it ingests a sequence of binary vectors, and then it has to reproduce those at the output in order. Okay, so you can see it's sort of an operation here. So at each time step, it's writing each input to different memory locations. So there's the input. It's accessing a single memory location and putting in that memory vector in there, and then it is able to sort of increment the memory location over time, putting in the different binary pattern in each slot. And then when you get to the output, when it decides to output, it then starts reading back from each of those memory locations one by one, and therefore essentially reproducing that same binary pattern at the output. And you can see it running here on sequences of sort of increasing length, and you can see there's a few errors that start to creep in when the thing gets really long. Because everything's soft, sometimes things will get distorted as to what gets stored in memory, or whether it should be reading or writing and things like that. But just to show you that an LSTM does far worse. So this is the LSTM trying the same sequences, and you can see that it does pretty well for these small ones, but then once you get to the longer ones, it does okay initially, but then it really just has no idea what's going on. Okay, as you can see, the neural Turing machine is doing a lot better. And they did, they applied it actually to a bunch of different tasks, like copying, doing sort of simple m-gram modeling, and also some sorting task as well. So this is a pretty cool model that from the DeepMind, and they, people have tried to build extensions on it. So for example, people have tried to train this with a discrete memory interface rather than a continuous one. But then the so-called reinforcement learning neural Turing machine, that's an interesting sort of extension of that. Okay, so what I'm going to show you now is just a series of works that sort of take some of the ideas in these models and actually apply them to a whole bunch of different sort of settings. So one, this is one I mentioned earlier, this is RNN search. So the idea is, the problem is machine translation. So this is a little example where they're trying to translate between English and French. And what they call attention is essentially the same thing as I was referring to in the memory network, where you're essentially attending to, in the memory network, you're attending to different memory vectors. Here, you're attending to different portions of the encoder state. So that is, you read in a certain sentence in one language, and when you're decoding, you're going to attend to different portions of that input, of the encoder states, when you're doing the decoding operation. So the basic idea is that when you're trying to translate a particular word, you don't want to use the entire input. You only want to look at sort of the relevant words in the other language. So, and you can this is a sort of matrix showing that attention. So if you had a completely uniform attention, this matrix would be completely flat, but when they actually, in a trained model, you can see that it's correctly kind of aligning effectively different words in the two languages. And that when you get certain phrases here, like the European Economic Area, that whole group, the ordering of the words is flipped, and you can see that the attention correctly picks that up. So you can see this is why it's the orientation's off, diagonal here. And in practice, this does help. So in these language translation tasks, you can measure something called a blue score. That's what the y-axis is. And then you have different lengths of sequence. So clearly, when you have longer sentences, it's going to be harder to translate effectively. And you can see that the standard models, which is, I guess, these two curves here, beyond a certain sentence length, they start to degrade. But with this model, where you can attend to some portion of the input when you're doing the translation, you can see that the performance remains kind of constant, independent of sentence length. Now, so that was obviously a sort of one-dimensional attention over different words in sentences. You can also have spatial attention. It's the same idea, just in 2D. So this is a little problem here of generating sentences for given images. So this is when you're going to train the model to sort of look at this image and then produce a sentence. And what's nice is that you can actually, for each given word, you can go back and see what the attention vector, or the attention map, as it were, the two-dimensional map is for this particular word. So you can see here with the word frisbee, it's actually attending to that portion of the image. It's not actually looking at the background or some irrelevant thing like that. Okay, so that, the dog is standing on a hardwood floor. Well, it's not exactly standing, but when you look at the word dog, you can see it is actually picking out the dog's face, and so on. And so this is, again, the same sort of idea, basically. So you can think of the memory network, really, as a kind of multi-stage attention model. You're just attending to different portions of the input as you go up. This is also doing the same sort of spatial attention idea, but now you're doing it on video, so you can attend to different portions of the video sequence, depending on. So obviously, over time, the camera's looking at different bits of the scene, and when you have the textual description, you can see that the word man, it's essentially attending to this portion predominantly of the video. You can also do the same sort of, just going back to this sort of the one-dimensional attention, you can do the same sort of thing for speech. So this is going from some of the raw speech waveform to some some phonetic units. Yeah, so it's the same sort of idea as one of those previous models. And then the final one I wanted to mention was where this is an interesting model called a pointer network, where the output is not like the attention essentially is the output of the model. So in this case here, they were trying to solve a bunch of problems like things like traveling salesman, And so they would train the model to attend to, essentially the next city and so on to reach the goal. And then the output of the whole network is actually just those essentially attention vectors saying which particular item that the model selected at each given time step. Okay, so I've got, I guess, 15 minutes left or so. So I wanted to spend the last little bit. So all these models are using a sort of continuous representation for doing the memory access. So what happens if you want to actually have a discrete setting? So it is possible to do that, and this was some work that one of my students, Wojciech Zaremba at NYU, did. So this was a slightly different task, but somewhat related. I mean, it's related to the binary addition thing we saw earlier for the stack RNN. So in this instance, we want to learn base 10 addition. So the idea is we're going to show the model at training time little examples like this. The 3 plus 5 is 8. We might show it some slightly longer ones like this, say 4 digits being added together. That's all we're going to give it. There's no further supervision. So I mean, supervised in the sense we are giving it the answer to the addition, but we're not telling it exactly what happened, between, to get to the 1 and the 3 to make the 4. And one thing we want to check is, of course, that we want to, from just these examples, sort of learn the underlying algorithm that mean we can, if we've got the right algorithm, we should be able to, at test time, correctly answer some enormous addition like this, okay? Now, clearly the model has never seen anything like this before, but if it has abstracted the right algorithm, then it should be able to correctly run and answer it. So that's our sort of check to make sure we're not kind of overfitting to these rather simple examples. And the point is that we do need to, in order to be able to sort of learn this addition operation, we do need to be able to have a bunch of quite complicated things happen, right? So we're going to be dealing with a memory interface which can only access a single symbol at any given time, and we have to have discrete actions that will move that kind of read head, if you like, over the different portions of our input. Okay, so it's going to effectively have to move that read head in a certain pattern. We're going to have to remember this carry operation and so on. And correctly sequencing all these things is actually quite intricate and complicated. And that's what we're asking the model to kind of learn automatically. So just to say, just as before, we're going to have a controller, something like a neural net, like an RNN, effectively. And the interface is going to be now this much simpler one than we looked at previously. I guess it's just a simple tape or grid where we can access a single symbol, in this case the symbol 5 at any given time step. And the controller can move this around, like move left, move right, or read the symbol. So those are discrete actions that we have to take. And obviously we need to take multiple actions in order to be able to produce an output symbol, which is going to make the problem hard. So this is just to show you different sort of interfaces we might have. This is a sort of 1D thing, 2D, and then the output's going to always be just a one-dimensional tape. Sorry, the red square has become misaligned. And so this is roughly the overall schematic. You've got some past, this is going to be your RNN type model. You've got some past state that is input to the controller along with your input interface, and you will be able to see what you output at the previous time step, of course. And you might have some type of other form of memory as well. But in this case, I think actually we're not going to, I'm not going to show any examples with that. And then that controller, of course, its state will be updated, which will pass on to the next time step. And then you will use that through take discrete actions to decide what to do at the output in terms of should you move the output head to the left or to the right, or should you output some kind of symbol. And so this is very roughly how it's going to work. So here you go. You've got a symbol, input symbol 4. The read head's at this location. The output is going to be null at this point. And then the action you're going to take is to move the input head down. Okay, so the next time step, the box slides down to look at the 6. Okay, so now the model can then read in the digit underneath, and now it should have enough information to be able to compute what the output should be. In this case, the digit 0. And of course, there's a carry in there as well, because really 4 and 6 makes 10. So in the future state, there should be some information there about the carry. And then the next action will be to shift this box over to look at the next column of numbers. So this is what we're going to try and, the model, we hope it will learn, at least for the addition example. We're actually going to try a bunch of different problems like copying, simply transcribing numbers between input and output, reversing a sequence, so we have to run over a sequence, and then when we hit a special symbol, we have to then at the output reproduce it backwards. you can imagine this is a little thing where we have to essentially, from a given location, we have to follow some instruction to reproduce numbers along a certain direction within the grid. These are the familiar addition problems that this is adding a pair of numbers, this is adding 3 numbers together, this is doing single-digit multiplication, and stuff like that. So the controller is going to be, this is a gated recurrent unit model from Kyung-Young Cho. This is a sort of simplified version of LSTM. And then we have, on top of that, a simple, so it's not a very complicated model. And actually, it turns out that you don't want to have too complicated a model for the controller. It's very easy to kind of overfit and come up with overly complicated algorithms, essentially. And on top of that, we've got a simple linear layer that will predict the output symbol. And we are going to give it a bit of an assistance. We will choose interfaces that are appropriate for the task at hand. So for that two-number addition, we will use a 2-dimensional grid. I mean, you could imagine doing it on a 1-dimensional tape, but it's going to make the thing naturally a lot harder because you'll have to move the read head around a lot more. Now, there are 2 outputs from the controller. So one is going to be a continuous output, much as we've seen before, of the symbol. So that's going to be a softmax over each of the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or null will be a valid output too. But then we will have this discrete action, which is moving those heads around. Now, that part we can't differentiate through, so we can't backpropagate to train up how the controller should operate the read head and the write head. And the other complicating factor is we're not going to get any kind of signal that we've got the answer right until we produce an output symbol. And as we saw, in order to do, for example, the addition, you have to make multiple actions. You have to move that little head, the read head, around on the input. And if it's a 3-number addition, it's going to have to take quite a lot of steps before you're able to produce an output. So in other words, we don't get a label at each time step. And this brings us into the scenario where we have to use something called reinforcement learning. This is what I was saying, effectively, that you have this discrete sequence of actions to produce a symbol, and the only label we'll get is whether we got the digit right or not. Okay, that's a simple 0-1 reward. So if we get the digit wrong, it gets 0 reward. If it gets it right, it gets 1. And if we do actually stop training on a given example if you make a mistake. So in practice, what we use is a form of reinforcement learning called Q-learning. So I don't really have time to sort of go into vast amounts of detail on this, but just I'll try and briefly summarize it. So the idea is you have some Q function, which is going to depend on the current state you're in and the action you're thinking of taking. And that's the estimated sum of future rewards. So that is, if we went, forward to infinity, what would be the total amount of reward I would expect being in this state and if I took that action. And this, in practice, is going to be a parametric function. So the input will be the input factor for this is going to be S, and it's going to output an A, and the model will be something like, in fact, this GRU model that I described. This is a form of gated RNN. So this will have parameters in it that we will learn by updating this kind of recursive relationship. So the idea is this is the sort of new version of the Q function, and this is the old function, and what you've got here is the current estimate of your Q function, and then this is essentially, if you take, this would be the reward you get if you move to the new state, and then this is the action which seems most promising under your current version of the model. Okay, so you've got this thing here where your current version of the model is going to tell you what actions you should take, and so the data. So in other words, the new state that you observe S prime will depend on the current parameters of your model. So it's a little bit, training these things is a little bit delicate, as you can see, because you're sort of, if this thing is completely crazy, and which it may be initially, then of course you're not going to take very good, the max over this isn't going to make much sense, and you'll take kind of somewhat arbitrary actions and so on. And you can also get into funny sort of oscillations where, it's updating, the model's being updated, which will affect this term here. So there's all kinds of tricks in terms of keeping perhaps an older version of this thing around to avoid these oscillations, and then only infrequently updating this QN model here. So R is the reward, so that's going to be the 0-1 business I was explaining earlier for the digits, and then gamma is a sort of discount factor, which is a sort of saying you prefer to have rewards immediate rewards rather than the ones in the future sort of somehow are worth less. So this typically is a number very close to 1 to give that kind of decay over time. All right, so when you train this thing, there's quite a lot of tricks involved, and in fact, the basic version of Q-learning doesn't work very well for this task of trying to learn these, abstract algorithms like addition and so on. So there's a whole bunch of little tricks that we used in practice, which I don't really want to go into in too much detail, but essentially we use something called Watkins Q-Lambda, which means you sort of, instead of just having a sort of one-step recursion where you go one time step ahead, you actually do multiple time steps, and this does work out reasonably well if you've got a fairly deterministic environment, which you do in this case because the state transitions are noiseless. So, and then we also have this problem that at test time you don't know how long the sequences are, so you actually have to sort of have some way of rescaling this Q function so that it doesn't depend on the sequence length, and then there's some sort of extra regularization term we use as well. So these are just some results. So these are the different tasks. We're trying most of the time we're using this GRU controller. Sometimes we try a very simple feed-forward controller, which is stateless. And this is just showing the number of units in the controller, the discount factor, which in this case is just set to 1. And this is the length of the test sequence. So it was trained on much smaller sequences, so it's never seen ones of this length before. And then this is showing various sort of options that we included, the bells and whistles effectively. So this, you can see that the copying task is fairly easy. What's interesting is actually the performance improves when you decrease the model capacity. So that's what I was referring to when it's easy to overfit sometimes with these controllers. But you can see these other tasks, it's not doing very well at all. But if you sort of put in a bunch of these, if you change the discount factor, and then you have this, or you have this dynamic version, or you have essentially these other bells and whistles that we came up with, then by the end of it, you are able to actually get these models to work quite well on these tasks. Okay, so it's using these discrete memory interfaces that are necessary to kind of solve these problems, and it's being trained with reinforcement learning. Sometimes you do need a curriculum. The curriculum is where you essentially start off by training on easier data, like for example, smaller sequences of numbers, and then once it succeeds on those, you then make them longer. So that is necessary for some of these harder problems. You can see this is an interesting case where the simpler controller for this reverse problem seems to actually help, whereas having the more complicated GRU controller kind of breaks it, and we never could get it to work in that setting. This is just showing you well, I'll skip over this slide, I guess. All right, so there's actually been a whole bunch of work here on trying to use these discrete, using reinforcement learning with some kind of discrete interfaces to these RNNs. So one good example would be that neural Turing machine I just showed you. You can combine that with a discrete memory interface instead of continuous, but then you have to use reinforcement learning. So that's actually some recent work by Wojciech as well with Ilyas Skeva. Then there's actually a couple of recent ones as well that came out really in the last few months, which are trying much the same idea of trying to learn these abstract algorithms like sorting and addition and so on. This one was actually somewhat similar. I mean, in this case, they actually supervised which actions you should take. So in this one, they didn't need to use reinforcement learning because in our case, we don't know what actions you should be taking throughout the model. So just to summarize this little piece, so effectively I've talked about learning these very simple algorithms with reinforcement learning. And it turns out actually, even if you do give supervision to the which actions you should take, it doesn't really improve the overall performance. It makes training a bit quicker, but it doesn't really improve the overall performance of the algorithm. And what we can see is that you can get these models to control these discrete interfaces, like these tapes and grids and stuff like that. And then at least for these particular problems, the capacity of the controller is quite important as well in order to be able to avoid sort of overfitting. Okay, so I'm just about out of time. So just to summarize what I've talked about, so what I've been really gone through is a bunch of different ways you can add explicit memory to neural nets. Okay, so we start off by looking at those stacks, and then we had this sort of the memory networks, which was this large associative memory, and at the end we looked at these grids where you had discrete actions when we were trying to learn those algorithms. So the continuous interfaces you can train with backprop seemingly quite successfully. and the discrete ones, you're going to have to use reinforcement learning. But it also seems at least possible, even though it's true that when we tried more complicated things, it did, the reinforcement learning did struggle. So it's not entirely clear how we're going to be able to, get to really complicated things with it. But I think the key message really, though, is that by adding these external interfaces and memory to the models, we can actually tackle new problems that you couldn't really do effectively before. And I think that's, it's quite exciting, and people are sort of, thinking about other things they might be able to plug into the neural nets too that would, take things to the next level. Okay, so I'm just going to stop there. I just wanted to thank very much all the people. I mean, I've talked about the work of many people, and so in particular, Saina and Wojciech, who are two students of mine and Yann's at NYU, and then a bunch of colleagues at Facebook Research. These people happen to be in New York: Arthur, Jason, Tomasz, and Armand. Okay.